Okay, so in the previous video, we learned three different approaches to implement and report the results of the hypothesis testing. It's like different ways to make the decision. And p-value and t-statistic approaches are actually pretty much the same, right? In the sense that they don't depend on the significance level. And it is choice of the significance level is up to you, so you can just make the decision based on them. However, critical value is slightly different because critical value, go back to the formula, critical value takes this form. What you need is the belief mu zero and significance level alpha, standard deviation sample size. So you need alpha to calculate the critical values, but you do not need the sample average x bar, right? So this is a different approach, and critical value is more convenient if you need to apply the same decision rule to different data. Like for example, like when you test like the study hours for like this year and next year and again, if you do the test every year, and then like critical value will be more critical value approach will be more convenient because you may use the same critical value every year again. You do not need to recalculate p-value each year. Just do the survey and take the sample average and make the decision right away. That will be more convenient in some situations. And I'm going to show you like in the next chapter where the critical value approach should be used. We will see that next time. Okay, so and then remember, when the significance level increases again, basic idea is more significance level means more percentage of rejection, so more likely rejection. So rejection region expands, so outside area must expand, and in other words, the critical values must be narrower, should narrow down closer to the null hypothesis. And if the standard error increases, then critical value also increases. They move away from the null hypothesis. In other words, the margin of error increases. You have to allow more margin because standard deviation is larger, which means there is more noise in the data. So that's the mechanism is pretty similar to the confidence interval. Okay, we learned three approaches. Now we are going to apply them to another example. Say, think about I-beams. So these steel beams are called I-beams because its cross section looks like uppercase I, letter I. So what we want to do here is so there are some standard sizes for the I-beams, and the smallest I-beam standard size is 80 millimeters. So of course it is very important to have the correct sized I-beams. So we are going to use hypothesis testing to check if your I-beams are correct, in correct size or not. So I would like to set up hypothesis this way. The null hypothesis is that the mean is 80 millimeters, but alternative hypothesis is the negation of the null hypothesis. Then you may understand it this way. X is the height size of an I-beam, randomly chosen I-beam. So you randomly choose an I-beam in your construction site and measure the size. And that is a random variable. So its population mean is mu. Population expectation is mu. And suppose that your sample size is 400. You measure 400 I-beams and you observe 79 millimeters as a sample average. So sample average is 79 millimeters and the standard deviation across 400 I-beams is 10 millimeter. So now you see that your sample average is slightly smaller than your belief. But I wonder if that difference is significant or not. So first thing we have to do is to standardize the difference. It's -1 difference. And in the t-statistic, you have to standardize it. Do it. All right. Stop it if you have not finished your work. The answer is, the difference is 79 minus 80 divided by s over square root n. And you know all the numbers. X bar 79, mu 0, 80, s. Standard deviation is 10, and sample size 400. So square root of 400 is 20. So it is easy to see that the answer is -2. -2 is the t-statistic. So now we are going to use the t-statistic approach first. Suppose that, and additionally suppose that, the significance level you are using is 1%. At 1% significance level, what is the decision rule? What is the rejection rule? Right? Think about the rejection, direction of the rejection, where you reject, and where is the cutoff value. You may use the previous slide to see the numbers, relevant numbers. Okay, so 1% implies 2.58. First of all, so rejection rule should be stated as t greater than something, absolute value of t greater than something. So A and C should be ruled out because of the direction of the inequality. Remember, t is the difference. And if the difference is too large, you are going to reject the null hypothesis. So to reject the null hypothesis, it should be this direction. And 1% is associated with 2.58. You may remember this. We have used this for the confidence interval too. And in our example, we obtained a t-statistic of -2. So do we reject it or not? We already got the cutoff decision rule. Then do we reject or not? The answer is no. That means, so the standardized difference is -2. And we set the cutoff at 2.58. That means if the standardized difference is in between plus minus 2.58, that we are going to treat as close enough to 0. The difference is small enough, close to 0, right? So -2 is, yes, it's included in plus minus 2.58. So we are not rejecting the null. That is the answer. B is the answer. Okay, so now, so what happens if you increase alpha to 10%? Think about this. So far, we considered 1% significance level, and the result was not rejected. Threshold was 2.58, t-statistic was -2. What happens if you increase alpha? So when you increase alpha to 10%, what changes is t-statistic does not change. That's the point. T-statistic does not change, but this number, plus minus 2.58, should change to plus minus 1.64. So now the difference must be much smaller for the belief to be accepted. In here now, it becomes 1.64. So -2 is outside of the thresholds, right? So the null hypothesis must be rejected. So that's how it works in the t-statistic approach. When alpha changes, the threshold should change, and you just compare the standardized difference with the threshold. And now let's move on to the p-value approach. So when t-statistic is -2, let's calculate the p-value. To calculate the p-value, of course, you need Excel. And imagine normal distribution and you observe -2 here. But don't forget to calculate the positive side. There is equally likely outcomes on the other side of the graph. Okay, the p-value is calculated this way. So our t-stat was -2. Then the p-value should include probability smaller than -2 and probability greater than 2. So the sum, and both probabilities are equal. They are equal. So the total probability, including both sides, is 4.55%. Okay, that is the p-value. That means if you rank the outcomes from the most unlikely to the least unlikely, then your observation is top 4.5% rank, right? And then given this p-value, among the common choices, 1, 5, or 10%, at what significance levels H is rejected, H null is rejected. So when, what significance levels can reject the null hypothesis? Think about that. So remember, in the p-value approach, we reject the null hypothesis if the p-value is smaller than the significance level. So in other words, so I said p-value, so this means your outcome is top 4.5% unlikely. But if the p-value was 10%, that means you are going to reject top 10%. So your p-value, your outcome is included in there. So that means p-value, to reject the null hypothesis, your significance level must be greater than the p-value. Among those three, only 5% and 10% can reject the null hypothesis. If you choose 1%, then you are rejecting only 1%, so 4.5% will be safe. Okay? That's how we make the decision based on the p-value. And by the way, as you can see, the p-value approach results are equivalent to the t-statistic approach. You can compare one by one. They must be the same. The results should be the same either you use t-stat or p-value approaches. All right. And finally, the critical value approach. Right. This is what I explained earlier. Now I'm going to fix the up. And also observe that in our previous examples, calculating p-value or calculating the t-statistic did not require alpha. So it was a good case, good examples, that they were good examples to study the role of alpha, the significance level. So we studied what happens if you change alpha, like, and compare different values alpha. But now in the critical value approach, you have to fix alpha to calculate the values. So I am going to use 1% and use 1% alpha and find the critical values. This algebra is quite similar to the algebra for the confidence interval. Remember, the formula for the critical values take this form. It's centered around the belief, and you allow this much margin. Margin is exactly the same form as the confidence intervals margin, right? And we use 1%, and 1% is associated with z alpha over 2 of 2.58. So 2.58, when you use 1%, 99% confidence level or 1% significance level. So same number as the confidence interval. Standard deviation, sample size, we all know them. So just simple algebra. So upper critical value is 80 plus this much margin. And lower critical value is 80 minus this much margin. So we get this, right? And then remember, in this calculation, we did not use this observation. 79 was our observation. Then given these critical values, can you reject the null hypothesis when you observe 79? The answer is no, because so the critical values are given. So that means if your sample average is in between those critical values, you are not going to reject the null hypothesis. But if the sample average is outside of the critical values, then you reject. In this case, 79 is greater than the lower critical value. So you cannot. So 79 is in between those two critical values. So you do not reject H naught, H null. And also, this result is consistent with our p-value or t-statistic approaches. They are designed to be equivalent to each other. Okay. So now change the critical value, change the significance level to 10%. Then how the critical values change? What is the new critical value? So when alpha changed to 10%, earlier the critical values were 81.29 and 78.71. Now this part changes. So 10% implies 1.64. Top 5%, bottom 5% implied 1.64. Plus minus 1.64 is used, and margin is recalculated this way, but the center is the same. With the same center, based on the belief hypothesis, you calculate the margin and add and subtract. Then you get these. And now you can see that you observed 79. Now, from this new critical value, lower critical value is greater than your observation. So your observation is lower than the lower critical value, outside of the critical values. So you have to reject the null hypothesis. In other words, compared to the earlier critical values, the critical values became narrower when you increase alpha from 1% to 10%, because 10% will reject more than 1%. So that means you have to make it tighter. The critical values are closer to the null hypothesis, or the margin is much smaller so that you can reject more, right? So in that sense, the intuition, the mechanism is consistent across different methods. Okay, final numerical example. So in the end, by the way, one last remark. No matter what method you use, the result should be the same, right? And if not, something is wrong. Okay, so last question. Now, I'm going to change the question, change the hypothesis this way. So earlier, I believed that earlier the null hypothesis was that the I-beams are in the correct size. But now, I suspect the I-beams are smaller. So I assume that the I-beams are actually 2 millimeters smaller than it had to be. So my null hypothesis is 78. Earlier it was 80, but now it's 78. But I'll assume that the data are the same. I do not change the data. Then in this case, do you reject or not? Using the new null hypothesis, we do the testing. You may use either method, whatever you like, p-value, t-stat, or critical value. choose whatever you like, use 1%, and make a decision. Okay, pause the video if you need time. So the answer is, so let me just show you all the three ways. T-statistic. So observation is 79, belief is 78, standardized, then t-statistic is now 2. And because we choose 1%, the threshold, the cutoff is 2.58. Plus minus 2.58 is cutoff, so 2 is included inside, close to 0. So we cannot reject the null hypothesis. If you calculate the p-value is like the probability outside on both tails, and it's 4.55%, which is greater than alpha. So you are rejecting only 1%, but your outcome is 4.5% from the top. And critical values are given by these numbers. So 78 is the new center, and plus minus 2.58. 2.58 came from 1% significance level. So calculate the margin, and you get this. So from all of the three approaches, you cannot reject the null hypothesis. Null hypothesis is not rejected. So then what do I want to say here is this. Earlier, I chose the null hypothesis this way. AD was my null hypothesis, and this null hypothesis was accepted, not rejected. That means I would conclude that the I-beams are correctly sized. But later, I changed my null hypothesis and repeated the same hypothesis testing using the same data. And in that case, the null hypothesis was not rejected, which implies the other conclusion. I-beams are 2 millimeters smaller than the correct size. So what I want to say here is, we use the same data, but depending on your null hypothesis, the conclusions are totally different. So this is because of the structure of the hypothesis testing. Hypothesis testing itself is not neutral. Like, it favors the null hypothesis. So if you change the null hypothesis, then your conclusion, implication of the result, could be totally different. So you have to be careful when you choose the null hypothesis. Usually, like in many cases, the null hypothesis is automatically implied. So have to understand how to interpret the results. Okay. In the next video will be the last one. We have one more example, and it is about binary distribution. So see you in the next one. Thank you for watching.